So what we're going to discuss in this video, first we will talk about a clustering problem structure. So we talked about classification in several other videos. Now we're moving on to clustering. We're going to talk about what is clustering, and we're going to discuss the benefits of clustering and specifically HAC. We're going to talk about the process of HAC, the important concepts that we need to understand to be able to apply the HAC, and we're going to talk about the dendrograms, which are the ways to visualize the clustering that we have conducted. So the problem structure in clustering. So first of all, you need to understand that structuring, we work with unlabeled data. So unlike classification, where most type of techniques used labeled data to kind of infer the classes of the new observations that are not labeled, in clustering, we don't have any labels on the data. We just have the actual covariate patterns. And from those covariate patterns, we are trying to kind of find what clusters or groups could exist. So there is no definite answer if groups exist or do not exist, but we are trying to kind of investigate or explore whether some groupings exist or not. So for example, these are 5 observations with 5 covariates. So we have 5 covariate patterns. Covariate pattern is the pattern of the independent variables. So x1, x2, x3, x4, and x5. We have 5 patterns, so 5 observations, and we want to see if these patterns can be grouped together. What question we will be asking with clustering is which observations are more similar to each other. So for example, you can think about it as customer groups. We have 1,000 or 2,000 or 100,000 customers, and we want to see which customer groups are more similar in terms of some covariates that we are monitoring. This could be for targeted advertising or some other marketing campaign. So basically what we are trying to do is to kind of find underlying groups and then see if we can make sense of them or not. So for example, I have an example here that I'm basing on soccer or football players. So if we have 5 players and we have ratings from 1 to 5 for pace, shooting, passing, dribbling, and defending, and let's say we have a problem that we don't have budget to keep the 5 players in our team and we can only keep 2, but we want to make sure that we keep 2 that are kind of different from each other, or the most different from each other. So we want to find clusters of similar players so we can pick 1 player from here and 1 player from there and hence reduce our budget. So these are the things that we want to investigate with clustering. So what is clustering in basic terms? Clustering is grouping observations together such that observations within a group, and this group we call a cluster, are more similar to each other than observations in other groups. So let's say we end up with 5 or 6 groups. We expect that the observations in group 1 are most similar to each other than observations in group 2 or group 3 or group 4. So within each cluster, the observations are similar. Among clusters, the observations should be dissimilar or a little different. So let's envision this in a 2 covariates case, in a 2-dimensional variable case. So if we have a bunch of observations on x1 and x2, and as we said, these do not have any labels, they do not have anything except the x1 and x2 value, and they are kind of scattered like this, we might think that these are more similar to each other, these are more similar to each other, these are more similar to each other, and hence we can infer some classing that we create as an outcome of the clustering. So if you remember, in a classification problem, we started with the classes of the training data, and then we try to predict the class of a new observation. So that was classification. In clustering, we start with covariate patterns, so values for the independent variables without an outcome variable of interest, and we try to kind of distribute these into groups. So what are the benefits of clustering? The most important benefit of clustering is that it allows us to explore our data. So remember, we're given a bunch of covariate patterns, just values for the independent variables, but we don't know anything about an outcome variable, or even sometimes we don't understand what we are trying to do exactly. So it helps us explore the data, see if different groupings exist. Let's say if we are in the US and we have covariate patterns on different types of assaults, for example, in different states. We want to see what states are more similar to each other, so we implement policies in these states that are more strict or so on. So it helps us explore the problem and understand what we want to do out of it. It helps us detect any hidden grouping. So many times there are groups in the data, like for example the customer groups. Let's say we are in Amazon, we have millions of customers, but we don't know which groups they follow, so we cannot target them with discounts, with advertisements. This helps us detect some hidden groupings. It helps us to get insights on the numbers and the structures of groups. So for example, maybe I don't know how many customer groups I have, but this could tell me very simply that you have 5 very distinct customer groups, and hence you can create 5 strategies to target these customers. It's a really good pre-processing technique that you can do to pre-process data for further analysis. So once you have these groups, you might want to implement different classification techniques for each group. So let's say if we are trying to solve a classification problem, but we want to start with clustering, it might increase our accuracy to create clusters, and then within each cluster create a classification technique to solve it, whether neural networks or whether KNN, and this will allow us to have different hyperparameters for each cluster depending on the best correct classification rate of each cluster. And it helps us to reduce dimensions, because think about it, we are looking for observations that are more similar, so we might end up finding that some of the covariants don't distinguish the groups very well, so it might be wise to just drop these and reduce our data. So these are the benefits of clustering or solving a clustering problem. Now, clustering have different types. So there is a partitioning clustering, and there is an agglomerative clustering like the hierarchical agglomerative clustering. Today we will be talking about HAC. So in HAC, think about a problem, let's say with 5 or 10 observations. Initially, every observation is its own cluster. So what we are trying to do, we're going to start from a bottom-up approach. We're going to look at every observation, and then we will start grouping the more similar to each other until all of our observations end up in one cluster. So we will start with each observation being in a cluster by its own. Then we will start calculating the distance between the current clusters, which are the current one single point observations. Now, the ones with the shortest distance, which are the ones that are most similar, we will join them into a new cluster. And then we will repeat step 2 and step 3 until all of our observations end up in one cluster. Because think about it, you will start joining, because for example point 4 and 5 are closest, you will join them in a cluster. Now you will have 1, 2, 3 and 4 and 5 are in one cluster. You will check which of these new clusters are closest, you will join them, then you will do the same until all of your points 1 through 5 will be in a single cluster eventually. So we talked about important concepts, which are distance and linkage. So distance is a metric to measure the dissimilarity among covariate patterns of 2 observations. So let's say one observation is X and the other observation is Y, and each has 5 covariates or 10 covariates. We want to have a measure that will tell us how different they are from each other in terms of these covariates. So this measure, or this distance metric, has to satisfy a few rules. The first one is that it should be non-negative. So you cannot have a negative distance. It's either 0 or 1 or 2 or 1.5 or whatever, but it cannot be -1, for example. So it should be non-negative metric. It should be symmetric, where if I'm calculating the distance from dxy, or denoted dxy, it's going to be the same as the distance from y to x, which is denoted dyx. This is kind of intuitive. It should satisfy the triangular inequality, which means that if I'm taking the distance between 2 points, it should be equal or shorter than the distance between those 2 points with a point in the middle. So if you imagine a triangle that has x, y, and z, the distance of x, z plus the distance of z, y should be either bigger or equal to distance from x and y. It cannot be smaller than the distance from x and y, because the distance between 2 points should be the shortest path. And finally, the identity of discernibles, which is very simple. It says that if the distance is 0, then the covariate patterns are exactly the same. Then x equals y, basically. So if you think about it, if I'm taking the distance from a point to itself, it's going to be 0. So I know that this point is 1 point. And also, if I have two observations with the same covariate patterns, I expect to have a distance of 0. So these are the important features a distance matrix has to satisfy. Now, what are some common distance metrics? And I'm not going to go into the formulas because you can easily find them on Wikipedia. So we use the Euclidean distance, which is the most simple distance metric. Sometimes some variables, imagine if we have 10 variables and some are more important than others, I want to multiply my distance metrics by a weight. So I want to take a weighted Euclidean distance. Let's say I want to add more, let's say, weight on x1 than x2. And these weights should sum to 1. I can do the Mahalanobis distance, which we also discussed in a previous video. You can use the Manhattan distance. You can use the maximum distance. And all these are basically distance metrics that you can look up. But basically, their idea is that they take the covariates and they create a function from these covariates of the 2 points and measure the distance between those 2 points. Now we go to the other concept, which is linkage. So distance, if you envision it, it was the distance between two observations where each had a covariate pattern that was associated with it. Linkage, on the other hand, is a measure of the dissimilarity between clusters. So let's say a cluster has 5 points, another cluster has 6 points. Now I want to see if these clusters are close to each other or they are far from each other. So I have a linkage criteria or a linkage function that will tell me if I should link those two and they become a single cluster or not. So basically a measure of dissimilarity among clusters with more than one observations as a function of the distance between the observations in each of the cluster. So the function is going to be depending on the covariate patterns that exist for the observations in each cluster. So I'm going to take pairs and I'm going to start measuring distance, and then I'm going to make a decision. So what are the common linkage criteria? The complete linkage, which looks for the maximum distance between all pairs. So let's say I take group cluster 1 has 5 points, cluster 2 has 5 points. I will create pairs, so each point will be paired with the other 5 points, so I'll end up with 25 pairs. And then I will check the maximum value for the distance, and I will call this my linkage metric. So this will tell me the dissimilarity of the two clusters. So this is the complete, and it's very strict. I will, even if there are 2 points that are close to each other, let's imagine the clusters are being like this, and I have a point on the tip and a point on the tip. They could be close to each other, but I'm taking the maximum distance between those two clusters. On the other hand, I can take the single linkage, which is a little more flexible. So if the minimum distance between all pairs is close enough, I will end up joining the cluster. So I'm taking the same 25 pairs, but instead of looking at the max, I'm looking at the min. And based on the minimum value, I'm either joining them or joining other clusters. The average linkage is somewhere in between. It's not the maximum, it's not the minimum. It's actually taking the average of all those metrics that we calculated for every pair, and then it's making the decision based on that. The centroid linkage is basically looking for the center of each cluster, and that center is done by averaging all the points in that cluster. So basically I'm taking the x1 value for all the points, I'm taking its average. I'm taking the x2 value for all the points, I'm taking its average. So I'm ending up with a new point that's going to be in the center of that cluster, and I'm measuring its distance from the center of the other cluster and making my linkage decision based on that measurement. So these are the type of measurements we are discussing with linkage criteria. So the important concepts in hierarchical agglomerative clustering are distance, which measures the distance or the dissimilarity between two observations, and linkage, which measures this dissimilarity between two clusters. Okay, now let's move to dendrograms. So dendrograms are the very interpretable way of graphing a clustering outcome. So basically it's a graphically a graphically interpretable description of the hierarchical clustering that we have done. So it basically has two main dimensions. It has the distance, which we talked about, and the linkage, because these are the two important concepts in hierarchical agglomerative clustering. We're talking about distance and linkage. And as we said initially, we start with the observations. Let's say we have observations A, B, C, D, and E, and we want to see which from these are most similar on which distances. So we will start our process, as we mentioned, that with each point being on its single cluster. So A is a cluster, B is a cluster, C is a cluster, D is a cluster, and E is a cluster. And then we will calculate the distance. So we will calculate the distance from A to B, from A to C, from A to D, from A to E, then from B to C, from B to D, from B to E. And we will calculate all these distance pairs, and we will join the ones with the smallest distance. So eventually, at some point of distance, which is that smallest distance, 2 points will join. And then we will move a little bit and we will see that more points are being joined. So our dendrogram will look something like this. So basically here, what we can do from the dendrogram is we know that A and B joined the first, so they are the most similar. So they joined at this point, which will give us a value for the distance that they joined at. And then C and D joined at this point. So if I cut my dendrogram here, I'll end up with 3 clusters. The first cluster is going to have A and B, the second cluster is going to have C and D, and the third cluster is going to have E. And eventually all points join together at this distance. So here I will have labels or tick marks for the distance. Let's say, for example, these joined at distance 5, these joined at distance 12 or 13, these joined at distance 15 or 17, and all points joined at distance 20. So my linkage is shown by linking basically 2 observations or 2 clusters, such as this case. And my distance is the horizontal axis. You can have a dendrogram either vertical or horizontal, but it's the same idea. So it could be switched, where distance is actually a vertical measure and linkage is shown on the horizontal axis. What we call these points, which are the singleton clusters, which have a single observation, are the leaves of my dendrogram. And every branch is a clade, but you can just call them the observations and the branches, or whatever makes you comfortable. But the idea is basically this. So what I can read from the dendrogram is the point where every point joined a cluster or joined with another point to create a cluster. And I can read which clusters are joined together earlier than the others. So I know which clusters I have. So I can end up solving this clustering outcome with 5 clusters, which are the single points, but this is not an interesting solution. And also with the full clusters, which as a single cluster, which is not an interesting solution. Usually I'm interested in somewhere in the middle. So I can end up with this point where I have 4 clusters. One cluster is A and B, another cluster is C, another cluster is D, another cluster is E. I can cut from here and have 3 clusters. One is A and B, one is C and D, and one is E. I can cut here and I end up with 2 clusters. That tells me A, B, C, and D are more similar to each other than they are to E. So I can have A, B, C, and D in cluster and E in a cluster, and this solution will give me 2 clusters. So at any given distance I choose, I can cut and see how many clusters I end up with. So in hierarchical agglomerative clustering, we're not deciding the number of clusters. We are letting the clustering that we conduct tell us the number of clusters. Basically, we can read the data. So let's say A and B and C made some actual sense. We know what they are. We can know that, yeah, actually true, A, B are more similar to each other, but C and D are not that similar. So we decide to cut from here. And let's say we decide that A and B are similar and C and D are similar, so we decide to cut here. Let's say that we see from the interpretable sense that those 4 are more similar to each other than E, so we decide to cut here, and so on. Now I created a small example just to understand dendrograms better. So I worked with the data of the FIFA 2021 players, and I took the players that had an overall rating of 90 plus. So the overall rating of 90 plus ended up with 12 players among the list of thousands of players. And I took the ones that have values for these covariates. So I only feel focused on pace, shooting, dribbling, defending, and physique. Let's say our problem again is choosing players that are similar so we can drop one and keep one, for example, if we had a team of all these great players. But basically, I ended up with 9 players and I conducted in R a hierarchical agglomerative clustering, and I ended up with these clusters. So now what we can know is that Muhammad Salah and Mani are more similar to each other than any of those other players based on the pace, shooting, dribbling, defending, and physique. We can see that they then join with Mbappe at that point or at that distance. Then Cristiano Ronaldo joined the cluster of those 3 at this distance. But actually before that, Neymar and Messi create a new cluster that is done at around 11. And then at 12, Cristiano Ronaldo joins those. And then these 2 clusters join together at point 18 or so. And then all of these join Lewandowski at, let's say, 21. And then they join Kevin De Bruyne at this point. And then at the end, that is very far point, all of them are joined with Van Dijk. So we can tell from this clustering that Van Dijk is very different from the others in terms of these covariates. We can tell that the most similar are Salah and Mani in terms of these metrics or these covariates. We can tell that Neymar and Messi are also similar to each other. And we can tell so many things from this clustering and then decide where to cut our dendrogram and what clusters we end up as an outcome of our clustering problem. With this, we end our hierarchical agglomerative clustering. We will go on to discuss partitioning clustering and we will implement some examples in R. So thank you for watching. If you like the video, please like it, subscribe, and share the video so everyone can benefit from our discussions in machine learning and data analytics. And good luck with your data analysis.